Ladies and gentlemen, warmly welcome. Wish you all warmly welcome to Aalto Mathematics and Art Colloquium. My name is Otaniemi. I'm the Vice President of Aalto and responsible for research. And it's my great pleasure to welcome you all to Aalto campus and to this colloquium. As you know, Aalto is a merger of three universities, leading universities in the Helsinki area. And one of the big potential that we have is that we have brought different roots and backgrounds together, and the multidisciplinary possibilities are one of the things that Aalto wants to exploit. And if you want to make this kind of a multidisciplinary happen, you need enthusiastic people and random encounters. And we are lucky to have such enthusiastic persons to drive and look at new possibilities. Kirsi Peltonen is one of the a person from the Department of Mathematics and System Analysis who has seen the potential in bringing together art and mathematics. Many of you know that Kirsi is organizing a very interesting Aalto course titled Crystal Flowers in Halls of Mirrors, Mathematics Meet Art and Architecture. And it has 30-something really excited students and making these random encounters possible. In connection with the course, Kirsi has also organized this colloquium series, which we now open. Of course, this means that Kirsi needs support. Luckily, the head of the department, Professor Olavi Nevalina, has been very generous. Also, the university has contributed, and now we're able to provide you something which we haven't seen in Finland before. We have our first speaker is Jeffrey Weeks. He calls himself a freelance mathematician. He's a geometric topologist and cosmologist. Dr. Weeks got his PhD from Princeton in '85 under the supervision of Bill Thurston. So this is sort of a person that has made big achievements in the area of topology. Dr. Weeks is known from his work on manifolds. Weeks manifolds that he introduced in the middle of 80s are well known in the mathematics. He's been awarded. He became a MacArthur Fellow in 1999 and won the Levy L. Conant Prize in 2008 or 2007. So we are very honored to have Dr. Weeks here and give us his talk on shape of space. As I've understood, that the talk is widely accessible, so I'm really looking forward to that. And I think that what we will see also is something that Dr. Weeks is also very well known is his software in this area, which is on topology and geometry software, which is widely used. So I'm confident that we will see some demonstrations of that. We discussed, and Dr. Weeks said that it's okay. It's perfectly. You're welcome to interrupt and ask questions anytime you feel. But we will have also a time for questions after the talk, and then after that we'll actually go and you're all welcome to join us for a cup of coffee and some sweets, and continue the discussion with Dr. Weeks there, and with also other people involved. There are actually quite a lot of students from Kirsi's course here who have actually done this in practice. So make mathematics or allow mathematics to meet with art and the architecture. So I think we're really have a really exciting lecture in front of us, and without further ado, I give the floor to Dr. Weeks.
Okay. Okay, thank you for the warm welcome. So first of all, everybody here okay? Sound good? Great. Okay, so it's a real pleasure to visit Finland, and it's a special pleasure to visit the Kristallisuus course that in advance, it sounded great in theory. Okay, we have students from math, art, and architecture all working together, but you never know how the reality compares to the original dream. So it was just an absolute joy yesterday to visit the class and see that the reality really does live up to this dream, to see students from very different backgrounds coming together and basically maybe sharing their passion for symmetry and related concepts. It was a joy to me, and I think it's a joy for them too. And most of all, it's a pleasure here to spend a week with my old friend Jouko Koskinen, in whom you'll find a talent for mathematics, art, and architecture all in one person. So, okay, let's get started. Okay. Our topic today is space. So here's a picture of deep space taken by the Hubble Space Telescope. There's an interesting story behind this picture that normally it's very difficult for researchers to get observing time on the Space Telescope, that literally every minute is precious. But the director of the project, as one of the perks of his job, was given a full 2 weeks to look at whatever he wanted. So as you might imagine, people were curious to know what he was planning to look at. So, maybe star formation or black holes, the evolution of galaxies. But do you know what he decided to look at? Nothing. Okay? He picked a little tiny patch of black sky up by the handle of the Big Dipper, Otaniemi, okay? And he pointed the telescope at that little patch of black sky for 10 days. And this is what he saw. Okay? So, as you can see, the universe contains galaxies of various shapes and colors. Okay, a typical galaxy contains about 100 billion stars. Not 100 million, but 100 billion. Okay, so it's less than the US government budget deficit, I know, but it's still a lot. But you have to remember that in this picture, you can see a few hundred galaxies, but it covers only a tiny part of the sky, about the width of this dime as viewed from 25 meters away. Okay, so if you were to look at the whole sky at this same resolution, you'd see, coincidentally, about 100 billion galaxies out there. So in rough terms, we're seeing about 100 billion galaxies, each with about 100 billion stars. So for sure, the universe is very big. But is the universe truly infinite? Or might there be some limit to the volume of space, some limit to the number of galaxies? In other words, might the universe be finite? Well, there's an old argument about this due to the Greek philosopher Archytas that said, well, if the universe had a boundary, you ought to be able to go to the boundary, stick your hand through, and find something on the other side. Now, Archytas interpreted that argument to mean that the universe must be infinite. But what it's really suggesting is that you don't expect the universe to have a boundary. Okay? And it turns out that being infinite and not having a boundary are two different things. But please be careful here. Okay? The Finnish word "ääretön" might suggest the definition, okay, avaruudella ei ole äärtä. But that is not the definition we want here. Okay? The definition we want is avaruudella on ääretön tilvuus. Okay, so that corresponds, I think, more to what the English word infinite would imply, and that's what we'll be looking at today. Okay? By contrast, The English words no boundary mean avrudella euleraya, okay, which is a different concept. Okay. And so what we'll look at today are some universes, some finite universes that have no boundary. But again, this äärilinen in the Finnish version here just means äärilinen tilavuus. Okay, nothing more. Okay, so we'll look at some finite universes with no boundary. I'd like to first drop down a dimension, look at some toy two-dimensional universes. Then once everybody's happy with the main ideas, then we'll come back and look at the real three-dimensional universe. Okay, so, whoops, sorry. There we go. Here, our toy two-dimensional universe is this patch of seafloor. Clearly it's finite, and at first glance it looks like it has a boundary, but really it doesn't. When the flounder swims off to the right, she comes back from the left. When she swims off the top, she comes back from the bottom. So this kind of universe is called a torus. Okay, so a torus, side to side, a torus is like a cylinder. Okay, so the flounder can swim off to the right and come back from the left. But the torus, top to bottom, it's like a cylinder in that direction too. So the flounder can swim towards the north and come back from the south. Now, if you take a piece of paper and you try to glue the top to the bottom and also glue the left to the right, you just get a crumpled mess. So we're going to forget that and stick with our software. Okay, so here's our torus. Now, it's a toy universe, so what do you do with a toy? You play games. So let's play some games on it. Okay, I'd like to warm up with a game of tic-tac-toe with all of us against the computer. Okay, so the first question here, where shall we go for the first move? Center, edge, corner? What? Is there a center? Well, let's pursue that thought. Is there a center? So say we go in a corner. Okay, and let's see, it's not crucial, but let me just turn up the sound here. There we go. Okay. Now, we went in what looks like a corner, but remember that torus side to side is like a cylinder, and you can take a cylinder and rotate it around. So we can take our torus and rotate it around as well. Or if we want, we can stop one square sooner. But the torus also is like a cylinder going top to bottom. So we can take it and rotate it in this direction. There it goes. Rotate it around, or stop one square sooner. So you wanted a center, so there we go. Okay. Where shall we go for the next move? We could go in the center again if you'd like. What do you think? Shall we try that? Okay, crucial moment here. If we're not careful, the computer will win. Yeah, so we want to go bottom center here to block the computer that way. And let's see. Okay. Where do we go to win? Yeah, to that top row, because we've got a potential 3 in a row there, so we can go here. There we go, 3 in a row. Good. Okay, to continue now, I'd like to propose a game of students versus professors, or more generally, younger people versus those middle-aged and older. If you're middle-aged and a student, you can pick either team. Here, before I forget, let me change this to human versus human and reset it. So could I please have one volunteer from each group? One student first, please. And if you're the volunteer, you don't need to decide the move. You just need to get a consensus from your team and come mark it down. Okay. Okay, so if you could get your team's consensus and mark it down. Okay, please. And could I have a representative of the professors and or people middle-aged or older? Or if you're younger than middle-aged and a professor, again, I guess you can choose either group. Could I have a volunteer, please? Want to be a volunteer? No. Oh. Well, I guess if we don't have a volunteer, it'll have to be Yoko then, I suppose. Okay, so you have to defend the honor of the professors here. Okay, students. Yes, if you want to move the board, you just can grab a grid line and move it around. Okay, students, good luck. Okay. Thank you. Thank you, Yoko. Okay, would you like to try one of the other games? Chess. Okay, chess it's a little more time consuming, so what I would propose is that we play a few moves and then move on. But if you would like to continue at home, remind me at the end of the talk and I'll put up a slide. These games are available online. They're free. You can download them for Mac or PC or iPad or iPhone. So remind me and I'll put up the address. Okay, but just to get started, we're playing the block of white pieces. We'll go first. The computer's playing the black pieces. It will go second. All the pieces move exactly as in ordinary chess, except for the pawns, which in the interest of symmetry, they move, if they're not capturing, they move one square vertically or horizontally. If they are capturing, they move one square on any diagonal. Okay, so what would you like for a first move? Move a rook. Okay, this one? Which way? Down. Okay. How far? Here? Okay. Oh, you know what I forgot to do? I think I forgot to set it back to human versus computer. Let's... Okay. What should we do now? We could grab the knight, we could move another piece. We could come down here and threaten the queen. Okay, so anyhow, you get the idea. And like I said, it can be kind of time-consuming to play this. Well, except when I play against the computer, sometimes the games end pretty quickly. But before we move on, though, I'd like us to do a crossword puzzle made specially for today. And okay, so the first clue here is kusta ja kaupunki. So we need a word that will go with kusta and is also a name of a city. Lhasa. Okay. How about the place where Buddhism, Taoism, and Islam were born? Yeah, okay, Asia. Okay. Oh, here's a good one, a history question here. The country where the fall of communism began in 1989. See, the younger people, they're going to have trouble with this one. So, Voila, good. Oh, oops, voila. How about when confidential information gets out? Okay, what else do we have here? Here's a good one. Romeon rakastettu. Kuka oli Romeon rakastettu. Julia. Okay. Tuo vuoro laivassa. Five letters, fourth letter is a T. Yeah. Vahti. What else do we have? Maalivahti in 5 letters. Yeah, Eska. Whoops. And I think we have only one letter left, one word left, and that's Helsingin uusin yliopisto. There we go. Okay. And again, yeah. So let's move on here. I have a question for you. Let's go back to the flounder here. And my question is, let's zoom out. The flounder, when she looks straight ahead, what does she see? Yeah, she sees her own tail. Her line of sight wraps around. She sees her tail. So from her point of view, when she looks straight ahead, she has the illusion of seeing a flounder sitting out here somewhere. Maybe she doesn't even realize it's her own self, but she sees a flounder out here. How about if she looks due north? What does she see? Yeah, again, her own tail. Her line of sight wraps around. She sees her tail. So looking north, she has the illusion of seeing another flounder sitting up here. Let's move this shell and have her look to the northeast. What's she see? Yeah, part of a crab, I guess. Let's see, your line of sight wraps top to bottom and side to side. We'll get that crab out of the way. And she sees her own tail. So again, she looks out here and has the illusion of seeing another flounder sitting off to the northeast. So in effect, she has the illusion of living in an infinite universe. So even though there's really only one crab, the flounder sees it in infinitely many directions. Okay, there we go. So we have this nice universe. So it's a finite universe, and it has no boundary. So that's what we were looking for, is a finite universe with no boundary. But unfortunately, this universe is only two-dimensional. So the question is, how can we take this same idea and use it to make a finite three-dimensional universe with no boundary for three-dimensional people like us? Any ideas? Yes, we want to add another dimension. So what will we start with when we add another dimension? Yeah, we could take a cube. So instead of starting with a two-dimensional square and gluing up the edges, we'll start with a three-dimensional cube and do the same thing. And in fact, it doesn't have to be a perfect cube. Any rectangular block of space would do. And in fact, if you ignore the slope of the floor here, we can use this beautiful rectangular block of space, which Aalto University has provided us with today. So we'll use that to make our finite universe. So here we are in this rectangular block of space. Now if I walk out this way, I'm not going to... Yeah, I'm going to come back in from the opposite side. Okay? If I walk towards the front wall, I'm not going to crash in here, but come in the back, exactly. And if I fly up through the ceiling. Practical spirit. Okay, so this sort of universe is called Oops, what does a flounder see? We did that. It's called a 3 torus, just as the flounder's world is called a 2 torus. Okay, so we're in our 3 torus here. We look forward, and what do we see looking forwards? Yeah, people say, yeah, we see the backs of our heads because our line of sight goes out the front, us in the back of the head. So in effect, we're looking forward and we're seeing another room full of people sitting in front of us. Okay, how about if you look to the right? What do you see? Same thing, your line of sight goes out, the right wall comes in the left wall, so we're seeing ourselves as viewed from the left, another copy of ourselves sitting over there. Yeah. How about if you look down beneath your feet? What do you see? Yeah. Yeah, your line of sight goes through the floor, comes from the ceiling. We see the tops of our heads, and in fact, they can see the tops of our heads really well. Okay. We can have the computer show us this effect. Let's see, where do I want to go here? Okay, so here we are inside a cube containing a single Earth. Let's expand it here. Okay, when we exit from this wall, we'll come back from the opposite wall, and we can cut a little window so we can see where we're going. So our line of sight wraps all the way around this finite space, giving us the illusion of living in an infinite universe. Okay. Okay, let's quit that. Okay, so that is called a 3 torus. And I think it's time to play a game in a 3 torus, but let me make sure I'm not forgetting anything. Yeah. Would you like to try a maze, but a maze in a 3 torus? Okay, so the goal here is to take the blue ball and slide it along to reach the white box. So let's see, at first there's not much choice here. Let's move it up here, and we'll move it across here. And now it looks like we might have a, no, we don't have a decision because this doesn't go anywhere. This might be kind of an easy maze, but we'll see how it goes. Okay, it's a different maze each time, so I don't know either. Ah, okay, here we have a decision to make. What do you think? Should we go down here or continue to the side and then up? Down, okay, so we go down and across this way. And let's see, going left goes nowhere, so we better go this way. And this way. Oh, this is working out. We didn't even have very many decisions to make in this one. There we go. Okay. Good. Thank you. So, let's look at some other possible shapes for space. So in 2 dimensions, we have the Klein bottle. So let's get ourselves a Klein bottle here. We'll go back to our Flounder and choose a Klein bottle. So side to side, the Klein bottle is just like the Torus. Okay? But top to bottom, it's glued with a flip. Okay, so anything that goes out at the upper right comes in at the lower left, and vice versa. Okay. Now the Flounder, if she swims up the center, she's going to come back in at the center, but what's different about her? Want to see that one again? So here she is originally. Here she is afterwards. Yeah, she's her mirror image. She got flipped when she went across the top there. Okay, would you like to try a game in a Klein bottle? Suggestions? Billiards. Okay. So, would anybody like to come give it a try? So I think we're still playing against the computer here. Yep. Okay. Anybody want to give it a try? No? Okay, well, here. Well, we're really in trouble then, because that leaves me as the only one to shoot here, but we'll see how it goes. Oh, almost. Yeah. Yeah, even the computer misses sometimes too. Okay, maybe we could. No, we can't get the red one. Let's see. Go for the white one, the yellow one there. Oh, a combination shot. Okay, let's try. Oh well. Oh well. Okay, well, we have some ground to recover here, but we'll... Thanks. Okay, so good job, computer, there. Okay, before we move on, again, we have a crossword puzzle made especially for the occasion here. And this one, it's in a Klein bottle, so things are a little different. You'll notice there's that yellow arrow. And let's fill in a word, then I'll tell you what the arrow means. So the clue is uroshevonen. Ori. Okay. And now the reason that yellow arrow is there is that it's telling you which way to read the word. So what's going to happen if we push the word past the top of the screen? Yeah, it's going to come back reversed. So that's why you need the arrow, so you know whether to read right to left or left to right. Okay, how about altava käsi? Apu. Okay, and let's see, maybe we should go straight to the long word here. So going downwards, I hope everybody knows the answer. Suomalainen tiedekeskus. Heureka. Okay. And there we go. Heureka. Okay. If you haven't visited there, by the way, you should. Okay. Let's see. What's left? Okay. Here's a word going right to left in this case for teorian sisko. So you do in science. Half the story is you make theories, but you're not done when you make a theory. What stage comes next? Yeah. Cool. Okay, and last but not least here, the ratio of a circumference to the diameter of a circle. P. There we go. Okay. Good. Okay. I have another question for you. And we go back to our flounder, and we zoom out. So in the Klein bottle now, what does the flounder see if she looks straight forward here? Does she see the pink shell or the red shell? Yeah, it kind of looks like she's going to see the pink shell, but we're in a Klein bottle here. So we've got that flip. So because of the flip, let me have her look better angle. So whoops. Because of the flip there, when she looks straight forward, she's going to see the red shell. So just like in the Taurus, the flounder has the illusion of living in an infinite universe. Only this time, the pattern of the images is different. Okay? And the pattern of the images reveals the shape of the space. So an observant flounder could tell not only that her universe is finite, but she could also tell whether it's a Torus or a Klein bottle. Okay? Okay. Let me make sure I'm not forgetting anything here. Okay, yeah, let's get back to three-dimensional space here. This one. Okay, so here we are in a 3 torus, just like before, only now we can take the Earth and drag it through the walls. Okay, now if we switch from the 3 torus to Klein space, then side to side the walls are glued just like in the torus. But top to bottom, they're glued with a flip. So if we take that Earth and push it up through the ceiling, what's going to happen to it? Yeah, it's going to come back as its mirror image. So there it is. Let's see, we can move it a little closer. So we're looking at the Pacific, then Australia, then Asia, then Africa. Okay, Finland's in the Far East now, then the Atlantic, then the Americas. Okay, let's take the Earth here and, whoops, I'm sorry, if we push it up through the ceiling again, what happens? Yeah, it flips again, so we're back to normal. Okay, I'd like to show you one other space that has no analog in 2 dimensions. Okay, in this space, the walls are glued just like in the torus. The floor and the ceiling are glued just like in the torus, no flip. The difference now is that the back wall is glued to the front wall with a 90-degree rotation. Okay. So if we take this Earth now and push it out the front wall, it comes in the back wall on its side. Okay. So let's park the Earth over here and go for a little flight. So what's going to happen when we fly through the front wall? Yeah, we're going to turn. We're going to go out the front wall and come in the back wall, rotated 90 degrees. Let's do that. Okay, there we go. We just came in the back wall, so there's the original floor on our right, the original ceiling on our left. If we go through again, what's going to happen? Yeah, it'd be 180 degrees now. So there's the original floor above us, the original ceiling below us. If we go through again, yeah, we'll be rotated 270. So there we are, original floor on the left, original ceiling on the right. How about if we go through again? Yeah, 360, which is the same as 0. So we're back the way we started. Floor down there, ceiling up there. Question, what will we see if we cut a little window in the wall? Yeah, so we'll cut a little window. So even though we're still flying around this finite universe, we have the illusion of infinite space. So the repeating images tell us the space is finite. The pattern of the images tells us the shape of the space, whether it's a torus, a Klein space, the space with the 90-degree turn, or something else. Okay, so I think we are ready to go on to the real universe. Make sure I'm not forgetting anything. Okay. Whoops, we've done that. Okay, so to test whether the real universe is finite or infinite, at first glance you might think, well, this is easy. We just look out into space and see whether we can see repeating images of the Milky Way galaxy. But it's harder than you might at first think. So what makes it hard? Why can't we just look out and either see repeating images or not? The speed of light. How does the speed of light enter into the picture? Yeah, we're looking into the past because it takes that light a long time to get here. So, oops, hang on. Okay, so we're looking into the past. We look out into space. We see nearby galaxies as they were recently. We see more distant galaxies as they were further in the past because it takes the light longer to reach us. We see really distant galaxies as they were just forming from clouds of hydrogen gas. And if we look beyond that, we see the primordial plasma from which the hydrogen condensed. Now, that plasma is opaque, so we cannot see any further. Okay, but please don't feel too bad about this, because we're seeing back 13.7 billion years. The beginning of time is only 380,000 years beyond that. So we're looking out and we're seeing 99.997% of the way back to the beginning of time. Okay. Well, this is true no matter which way we look. We can look any direction into space. We're looking out and seeing into the past. So in effect, our horizon is this huge sphere filling the whole sky with us at the center. Okay. So great. Does this mean that we can go outside this evening, wait for another one of those beautiful breaks in the clouds to come by and look out into the sky and see this plasma on our horizon? Well, yes and no. Okay, that plasma really is there. Okay, the catch is that the radiation we receive from it arrives not as visible light, but as microwaves. Okay, so if human eyes were sensitive to microwaves as well as to visible light, then the night sky might look something like this. Okay, so we'd look out, we'd still see nearby galaxies as they were recently. Then we'd see more distant galaxies as they were further in the past. Then we'd see really distant galaxies just being born from clouds of hydrogen gas. And then behind everything, we'd see the primordial plasma on our horizon sphere. Okay, excuse me a moment. Just water. So the temperature fluctuations in the plasma, the temperature fluctuations on the horizon are due to density variations in the early universe. Okay, so some regions were a little denser, some were less dense. The photons that reach us from denser regions, they do a little bit of extra work against gravity and arrive a little bit cooler. Photons coming from less dense regions, they do less work against gravity. They arrive a little bit warmer. So in effect, we're looking out and we're seeing density variations in the early universe. Now, you might be wondering, what does this have to do with whether the universe is finite or infinite? Well, we're getting to that part right now. Okay? So here's a cartoon picture of the primordial plasma superimposed on the modern galaxies that it evolved into. And this red circle, that represents our horizon sphere. Now, as you can see, there were more dense and less dense regions in the plasma. And in an infinite universe, those density fluctuations can be as broad as you want. But in a torus universe, the density pattern repeats, just like the images of the Flounder repeated earlier. So the biggest fluctuation you can have would be the distance from one image of a galaxy to the next image of that same galaxy. And in particular, on the horizon, the fluctuations can't be any bigger than what you see here. So in summary, in an infinite universe, you expect broad density fluctuations on the horizon, while in a small finite universe, you don't. Okay? So if we want to test whether the universe is finite or infinite, we just need to look at the sky with a microwave antenna and see whether we can see these fluctuations. Okay, let's do that. Okay. So In 2001, this Delta rocket carried the microwave anisotropy probe, Wilkinson microwave anisotropy probe into space. This is more easily pronounced as the MAP satellite. So MAP orbited the sun in synchronization with the Earth and observed the microwave sky for 9 years. This is what it saw. Now, the cool thing about this picture, this is our real horizon here. The cool thing about this picture is that it lacks the broad fluctuations you'd expect in an infinite universe, suggesting that the real universe could indeed be finite. Okay? More precisely, the broad fluctuations are weak at the 1 in 3,000 level, meaning that you could get such weak fluctuations even in an infinite universe just by chance, but only one time in 3,000. Okay. On the other hand, the fluctuations you see here, when you study them more closely, they don't really look like what you'd expect in a 3 torus either. Okay. A better candidate is the Poincare dodecahedral space. So what is that? Well, let's call one up. Okay, so the Poincare dodecahedral space, it's like a 3 torus, but it's made from a dodecahedron instead of a cube. So let's go inside. Okay, so you can probably guess now when we exit across one wall, we're going to come back from the opposite wall, and we can cut a little window to see where we're going. We can make the windows wider for a better view. Of course, in the real universe, Mother Nature doesn't show us the walls at all. So we'd see something more like this, and it would be up to us to figure out the shape on our own. So, in effect, the dodecahedral space, it's kind of like a 3 torus, but instead of having a universe based on a cube with images repeating along a cubic lattice, we'd have a universe based on a dodecahedron with images repeating along a dodecahedral lattice. Okay. Now, here's the kicker. A dodecahedral lattice cannot exist in flat space. Okay? Instead, it exists on a hypersphere. So it's kind of like we're flying on the 3-dimensional surface of a 4-dimensional ball. So this means that if the real universe really does have the shape of a Poincare dodecahedral space, it means that space is not only finite, but also slightly curved. Okay, here we go. Slightly curved. Okay, how curved is it? Well, think for a moment about spheres. You can have small spheres and large spheres. A little tiny sphere, like a ping pong ball, curves very tightly. A bigger sphere, like a basketball, curves more gently. A sphere as big as the Earth curves so gently that it looks almost flat. Now, it turns out that in order for the Poincare dodecahedral space to explain the missing fluctuations, the dodecahedron would have to be about 80% the size of our horizon sphere, which corresponds to a curvature of a little under 0.02 on this scale. Now, the original MAP satellite data, along with some other experiments, originally suggested a curvature of 0.02 plus or minus 0.02, so looked pretty good. Okay. Then in 2008, observers got some newer data that pushed the curvature estimate down a bit away from the values we're hoping for. But then in 2009, when researchers folded the Sloan Digital Sky Survey data into the mix, that pushed the curvature estimate back up again, suggesting, well, maybe the dodecahedral model was okay. And then, well, unfortunately from my point of view, but last summer, somebody did a study measuring curvature using gravitational lensing techniques, and in that preprint, they come up with a much tighter bound around 0, suggesting that, well, maybe the dodecahedral model isn't so useful after all. Okay. Even with the curvature down here, the universe could still have the shape of a dodecahedral space, but it would no longer explain the missing fluctuations, so there'd be no reason to prefer the dodecahedral shape over any other. Okay. In conclusion, the universe might be flat, or it might be slightly curved. It might be finite, or it might be infinite. The only thing we know absolutely for sure is that Mother Nature has more surprises in store for us. So thank you all for coming.
So now there's time for questions. Anything?
Before the first question, just so I don't forget, I promised to put up the address for the game. So if anybody wants to play the games, they're available at this address. And indeed, well, not as we speak, but this week, Yoko is making a Finnish translation of this. So if all goes well, at some point next week, I'll get back home and put it online. So there'll be Finnish included too.
Yep.
The universe, which would be plausible. So you can glue the cube and then the dodecahedron, but can you glue any other shapes in that similar way to get something which would be the shape of the universe?
Yes, okay. So the way the possible shapes, well, we want to look at candidates with constant curvature, because within our horizon, we observe constant curvature to, I think, about 1 part in 10 to the 4th. So you can either look at flat spaces or positively curved ones like spherical curvature, or negatively curved ones, which are, roughly speaking, hyperbolic or saddle-shaped. Okay, the candidates in each collection, the hyperbolic ones with a negative curvature are pretty much excluded by the curvature estimates so far have tended to lean towards positive, so there's not as much going on there. Amongst the flat ones, you can kind of get some fits, but not so well. The positively curved ones give better fits. The dodecahedral does the best. Then there's a triple of these called the space. The one made from a dodecahedron, when you looked at that picture, the symmetry group of things tiling around is actually called the binary icosahedral space. And there's similar ones, the binary octahedral, binary tetrahedral, and that binary octahedral one gives kind of the second best fit. And other things give lousy fits. Like there are other spherical spaces where you can take a lens shape and glue opposite sides, and it just gives a horrible fit. So there's that and a couple others that fit fairly well.
Further questions? Yep.
Thanks. What kind of curvature measure you use between different spaces?
The curvature measure?
Yeah, like Gaussian.
What this is, okay, what the scale is the way cosmologists think about curvature is general relativity is a geometrical theory of gravity. So it explains gravity as a manifestation of curvature in space-time, but it gives you this very nice result that the amount of curvature you have depends on the amount of mass and energy in the universe. And so what they do is they go out and say, well, how much mass energy, what density of mass energy does it take to make a flat universe? And that by definition is 1, okay? And then if you have more mass energy, that makes space spherical or positive curved. You have less, it's hyperbolic or negatively curved. For any astronomers in the audience, this is capital omega, is what I'm talking about here. So it's this nice scale. 1 is flat space. Anything beyond 1 is spherical. Less than 1 is hyperbolic. All that's going on here is I subtracted off 1 because for people who aren't astronomers, it kind of makes more sense to have 0 curvature correspond to 0 rather than have 0 curvature correspond to 1. But otherwise, this is the cosmologist scale of capital omega, saying the actual ratio of mass energy to the value needed for flat space.
Further questions?
How can you measure the curvature of the space? What
how do you
devices
measure? Yes.
or whatever?
Okay. The answer, regrettably, is indirectly. And in fact, measuring the curvature, you need a theoretical model of your universe. So I guess measurement sister is theory in this case. So you have a model for the universe, and you have 2 free parameters. One is the actual density of ordinary matter, and the other is the density of vacuum energy. So you have this sort of like an XY plane, a 2-dimensional plane for your possible combinations of how much matter, how much vacuum energy. Now, when you go to do an experiment, so say you look at the microwave background, you look at those fluctuations, that tells you something about where you can be for the choice of how much matter, how much vacuum energy, but it gives you some uncertainty, and it just puts you within an ellipse. So you get some band of where that experiment allows you to be. But then you can do other experiments. For example, you can go out and measure the amount of ordinary matter that you see. So that, it doesn't tell you anything about vacuum energy, but it does tell you how much ordinary matter you have. So there you get an error zone that runs vertically. So you've got another strip. So we have to be along here, we have to be along here. And the third thing people do is they look at distant supernovas and analyze how the light dims out from them. And by that, you can tell sort of whether space is focusing light or kind of unfocusing light. So that's another experiment. That gives you some other ellipse. And the happy thing is, if you just randomly put down 3 of these error ellipses, there's no guarantee that they should intersect. But in reality, you do 3 experiments, and they all 3 intersect in a consistent region, telling you, yeah, the experiments are probably good, and that tells you that the amount of ordinary matter and the amount of vacuum energy should be within that range. And then with your theory, you compute out how much curvature that corresponds to. So it's unfortunately somewhat indirect, but at least it seems to be working.
Time for, let's say, one question still. Any takers?
How does the age of universe affect the curvature? So if you have space-time, how can you show the student that, okay, here is this time and here is this time, and this is what we will get after a certain period of time?
Yeah. So as the universe expands, curvature, it looks flatter and flatter as time goes by, for the same reason as a sphere expands, a bigger sphere looks flatter than a smaller sphere. So whatever the initial curvature, it keeps looking flatter. Okay, so shall we break and continue the discussion by the snacks?
Yes, let's do that. Thank you very much. Let's thank the speaker again. Thank you very much. So thank you very much for the very inspiring talk. And then we'll continue this discussion over some coffee in the lobby. So you're all welcome to join us and talk to our speaker. Thank you.